Hi everybody, I'm Professor Rad, and in this video we're going to talk about type 1 and type 2 errors, as well as statistical versus practical significance. So far we've been talking about our hypothesis tests, and we've discussed the null and the alternate hypotheses, as well as how you can draw your conclusion. And when you draw the conclusion for a hypothesis test, you're essentially challenging a claim about a population, and you're using a sample mean to contest it. And we saw that if that sample mean is unlikely, then you would reject the null hypothesis and conclude your suspicion, the alternate. If that sample mean is likely based off of the null hypothesis, then you would fail to reject. And all of this is based off of the probability of your sample happening if the null hypothesis is true. So we talked about two different levels of weirdness. We had a 5% level and a 1% level. So if your sample had a 4% chance of occurring, then, if you're using the 5% level as your cutoff for weird, 4% would be unlikely, it would be weird. Whereas if you're using the 1% level, 4% would not be considered weird. Regardless, your sample had a 4% chance of happening, so it could happen, and that null hypothesis could be true. So when we conduct a hypothesis test, there is a probability of your sample happening that's non-zero, and so you could have just happened to have the weird sample that happened or didn't happen, and that can result in an error in your conclusion. So these are cleverly named type 1 and type 2 errors. So the names don't really help us identify which type of error it is. So let's investigate what they are. In a type 1 error, this happens when you reject when it turns out you shouldn't have. Okay, in other words, you happen to get a weird sample that was statistically significant, but later it turns out, yeah, you just got the significant sample, but the mean was actually true. So here's an example of that. It says a restaurant owner claims that less than $30 is spent on a meal at his restaurant. So he samples 32 random patrons one year and carries out a test of mu equaling $30 versus mu being less than $30, and he does this at the 5% level. And the p-value he gets indicates that he should reject the null hypothesis. In other words, this hypothesis test says, you know what? You can reject the $30 and say, yeah, people spend less than $30 at your restaurant. Now, later on, an intern reviews all the bills for the year. So the intern looks at the full population and finds the mean to be $30.02. So it turns out that the patrons actually spend slightly more than $30. They spend about $30. So we shouldn't have rejected this. So the restaurant owner must have just looked at a sample of bills that were less than 30, or he looked at too many or not enough of them. So when you conduct a hypothesis test at a particular level of significance, the probability that you're going to make a type 1 error is alpha. So in this case, because the restaurant owner used the 5% level, the probability that he would have made this error is 0.05. So it seems like if you're trying to avoid making a type 1 error, well, then you want to use a smaller significance level, right? So if he had used the 0.01 level instead, then there only would have been a 0.01 probability that he would have made this mistake. Or it's not a mistake, this error. So let's say the higher the alpha level, the higher the significance level, the more likely it is that you're going to make a type 1 error. So you might want to say, okay, well, that's great. Why doesn't everybody just use the 0.1 level? Let me introduce you to my friend, the type 2 error. Type 2 error happens in the opposite case, when you fail to reject, and it turns out you actually should have. So in this case, we have a test being made that the mean is 18, and the alternate is that the mean is more than 18. The conclusion that the null hypothesis should not be rejected at the O1 level is drawn. So we conclude, okay, the mean is 18, that our sample seems to support that. However, later on, it's determined that the true mean is 22. So it turns out it actually was bigger than the 18. So in this case, we have a type 2 error because we failed to reject the null based off of our sample, but it turns out that we probably should have. Okay, or not probably, we should have. This is that situation where, like, let's say I were to say to you, I think that everybody with rainbow hair has pink eyes. And if there's nobody with rainbow hair in the sample, then you can't contradict what I'm saying. Okay? So you would say, okay, yeah, you know what? I can't contradict you, so we're going to say that's true. And then you go out and you find another sample with somebody who does have rainbow hair and they have blue eyes. And you say, aha, this sample says that we're going to fail, that we're going to reject that now, and we're going to make our alternate statement true. So it just means that in this case, our sample happened to support the null, but that later on it showed that the null was actually not true. Now, the probability of a type 2 error is not as simple as just saying alpha, but the higher the significance level, the less likely it is that you're going to make a type 2 error. So in other words, if I'm trying to avoid a type 2 error, then I want to use a higher significance level. So if I want to avoid a type 2 error, I want to use the O5 level. You see the problem with what we said about the type 1 error? So with the type 1 error, the higher the significance level, the more likely you're going to make a type 1 error. So it's kind of like this balancing thing that's going on. If you create too high of a significance level, now you're more likely to make a type 1 error. But if you swing the other way and you use too low of a significance level, now you're more likely to make a type 2 error. Okay, so when you are, in the world deciding which level of significance to use, it's kind of a balance between which would be the worst type of error to make. So let's summarize that on the next page. So when choosing a significance level, it's important to be mindful of these two errors. Too big of an alpha and a type 1 error is more likely, but too small and a type 2 error is more likely. So that's why the O5 and the O1 tend to be used, because they've been found to kind of balance these different types of errors pretty well. All right, so in addition to the errors, we want to think about this word significant, because this is going to have a statistical meaning, which may or may not have I think of it like a plain clothes meaning, like a normal everyday human meaning. So it is possible to find a result that is statistically significant, even if it isn't practically significant. So statistically significant means that our p-value is less than alpha. Practically significant means that when you put this into action, does it actually make a difference? Is it like a significant difference? So let's investigate an example where this might happen. So it says a new method of post-operative treatment was evaluated for patients undergoing a certain procedure. Under the old method, the mean length of hospital stay was 6.3 days. In the new, it is 6.1 days. A significance test is conducted with mu equals 6.3 days, and mu is less than 6.3 days. We rejected the null hypothesis at the O1 level with a pretty small p-value of 0.002. So, are the results statistically significant? Remember, this question means, is your p-value less than alpha? That's what that question is asking us. So our p-value is 0.002 and it is less than 0.01. So yes, our results are statistically significant. So our explanation would be our p-value of 0.002 is less than alpha, which was 0.01. That's what it means to be statistically significant. So what this could mean is this test is done and maybe you're like, oh my gosh, this is amazing. This new post-op treatment is going to significantly reduce the length of stay in the hospital for our patients. So I'm going to go tell my boss and he's going to give me a big raise and it's going to be fantastic, right? And we'll begin to implement this new post-op treatment. So now let's see if the results are practically significant. It says, under the old method, the mean length of hospital stay was 6.3 days. In the new method, it is 6.1 days. So practically, people are in the hospital for 6 days and a couple of hours. That couple of hours, not going to make a big difference, right? So 6.3 days, 6.1 days, they're in the hospital for 6 days. So are the results practically significant? No. And that's because 6.3 days and 6.1 days are basically the same. So this is one of those things where when you are reading something that is telling you the conclusions of a scientific study, you have to just have your intense reading glasses on, I guess, because you have to be mindful of, is it statistically significant or is it practically significant? And ideally, we would have both for our results. We would have statistically significant results that would indicate a better post-op treatment. But in this case, this one's essentially saying the new treatment is about the same in terms of hospital stay as the old treatment. All right, so that's going to wrap it up for this video. In the next video, we haven't talked about how we find these p-values yet, so that's where we're going to be heading in the next one. So I hope you found this video helpful, and I will see you next time. Bye for now, everybody.